In this video, I'm going to talk about our paper titled Transformation Consistency Regularization, a Semi-Supervised Paradigm for Image-to-Image Translation, a joint work with Dr. Rafal Mantik. In recent past, deep neural networks have achieved immense success in a wide range of computer vision applications, including image and video recognition, object detection, semantic segmentation, and image-to-image translation. However, a fundamental weakness of the existing networks is that they owe much of this success to large collections of labeled datasets. Scarcity of labeled data has motivated the development of semi-supervised learning methods, which learn from large portions of unlabeled data alongside a few labeled samples. Consistency regularization, in particular, has shown to provide state-of-the-art results for image classification tasks. In principle, consistency regularization enforces a model's prediction to remain unchanged for an unsupervised sample when the input sample is perturbed. These perturbations can be of the form of image augmentations, adversarial noise, etc. However, applying consistency regularization in image-to-image translation is not straightforward, because images with varied transformations should have different predictions, unlike in the case of image classification. In this work, we propose transformation consistency regularization, which delves into a more challenging setting of image-to-image translation, which remains until now unexplored by current semi-supervised algorithms. The main benefit of our method is that it requires only 10 to 20% of labeled data to produce similar reconstruction results as a fully supervised method. The inspiration of our technique comes from the observation that in many image-to-image translation tasks, input and output images lie on different manifolds. We train a model using unsupervised images to draw insights about the input manifold and thereby provide a better mapping function to the output manifold. In this figure, at the top, we show how a baseline supervised model, which uses 10% of the training data for image denoising, fails to map some of the output images to the natural image manifold. However, our technique, which also uses only 10% of the labeled data, remaps the otherwise off-the-manifold images to the natural image manifold. Our method improves the mapping because it is trained on large collections of unlabeled data, which are transformed with an augmentation denoted by T in this figure. Our method introduces a transformation consistency regularization term. The term ensures that when we transform an input image or a patch using a geometric transformation, the prediction is consistent with the transformed prediction of the input patch. We randomly sample from a set of geometric transformations which reflect expected changes in image patches due to changes in camera pose. These include rotation, translation, scaling, and horizontal flipping. The loss function used for training our method constitutes of two parts. Firstly, we have the conventional supervised loss term. Here x and y are the input and output pair, and b is the number of supervised images per batch. Additionally, we have the transformation consistency regularization loss term, which is applied over the unsupervised data, denoted by U in this equation. Here R is the ratio of the number of unsupervised images to the supervised images in a batch while training. The overall loss is the weighted combination of the supervised loss term and R proposed term. It is to be noted that R transformation consistency loss term can be applied over supervised data as well without making use of the ground truth label Y. Here, we show the results for image colorization for the baseline model. incrementing the percentage of labeled data used for training the model. We observe a minor improvement in the performance by adding an additional image augmentation loss term. On adding the transformation consistency regularization loss term over the supervised data, we achieve a greater performance boost than image augmentation. Finally, when the transformation consistency regularization term is added over the entire dataset, that is, the supervised plus the unsupervised data, we observe a substantial increase in performance. We observe consistent trends for different image-to-image translation applications, namely colorization, image denoising, and image superresolution. Now, we swiftly run over some of the qualitative results achieved by our method for the above three mentioned applications. We can observe that our method requires only about 10% of the data in paired form, that is supervised, to achieve similar reconstruction results as the fully supervised model. Similar observations can be made on the task of image denoising and image superresolution. Now, we demonstrate the qualitative results of our semi-supervised learning-based method on movie applications. To begin with, we show the efficacy of our method on movie colorization. Our proposed method can go a long way in colorizing old movie clips when an artist is required to colorize a few frames only and the rest is handled by the network. We choose Blender Foundation's open source movie Big Buck Bunny for this task. The movie is divided into a train and a test set, each comprising of 510 and 43 seconds respectively. Out of the training frames, only 1% of the labeled image pairs is used, while the rest is fed to the network in an unsupervised fashion. In the middle, we show the results obtained by a baseline model that is trained on the supervised data, which is 1% of the training data. On the right, we show the results of our method, which again uses only 1% of the label data. The rest is fed to the transformation consistency regularization term. We can see that our method achieves an average PSNR gain of around 6 decibels. Next, we show the efficacy of our method for super resolution of movie clips using our semi-supervised scheme. This technique has immense applications in video recording, where a sensor bandwidth constrains the resolution of the frames being recorded. Our method can solve this problem by leveraging a few frames that are captured at a higher resolution in enhancing the resolution of the rest of the movie. For this application, we use Blender Foundation's open source movie Elephant Stream, which is also divided into a train and a test set, each comprising of 600 and 54 seconds respectively. At the top left, we have the ground truth high-resolution movie clip. At the top right, we show the results for the upsampling using bilinear interpolation. At the bottom left, we show the results obtained by a baseline model that is trained using only the supervised data. On the bottom right, we show the results of our method, which again uses only 1% of the labeled data. Our method achieves an average PSNR gain of 5.7 decibels.